we'll just discuss about the thermodynamics of electrochemical cells, or basically cells. Okay. Now think about it, when we write all this thermodynamics like Nernst equation, whatever, right? So there is a concept of reversibility, because without reversibility we cannot write anything. We discussed it, right? Usually for any irreversible or spontaneous reaction we cannot write this equality sign, right? So the question is, how good is this reversibility concept? Okay. First of all, like there can be many different type of reversibility. One is of course the thermodynamic reversibility. Okay. That we know what does it mean by that? That I will make a change, okay, in an infinitesimal way, right? So that basically, like we discussed about the pressure volume work, okay. So that work was basically to make it reversible. I was, for expansion work, I was reducing the weight little bit every step and increasing the weight every step very little bit, okay, for the compression work, right? Now the same concept is here also. Like we have to change the electromotive force of the potential, okay, very infinitesimal way. Then the thermodynamic reversibility will hold, okay. But before that, the question is whether there is any chemical reversibility or not. Okay. So what do you mean by that? Okay. Let me just give you an example. Okay. So I have suppose this cell, platinum H2, then H plus. This is the standard NHE. Okay. And then I have fluoride. So these two are in aqueous solution. And I have suppose silver chloride and silver. Okay. So this is a silver chloride electrode, okay, and this is a standard hydrogen electrode, right? So what, like, if we just do this reaction, okay, so what will happen is that it depends, of course, on the standard reduction potential. You can actually look at the all these respective values. With respect to platinum surface, what is this? This is 0 taken to be. Okay. And then the right hand side will be positive. You know that, right? It's basically E right minus E left. Now the spontaneous reaction will be something like this, right? And then we'll have basically AgCl. This. Okay. It should have reduction. So what I'll have is Ag plus Cl minus. So if I just multiply it by 2 and if I add it, then I'll have the total reaction. Okay. Now this reaction, okay, is supposed to, is a spontaneous reaction. But the thing is that if we want to make it reversible, okay, what we will do, we'll just apply an external voltage. Okay. So what will happen? Like the way I'm saying it right now is that suppose this is the platinum side, okay, and this is the silver side, right? So here I see that H plus is coming here, right? So I have excess electron here, okay. So I'll have an electron flow here. So in order to stop that, what I have to do, I have to basically use a negative bias, okay. And then what will happen if I just keep on increasing the potential, at some point actually this will stop, which is equivalent to the zero current, okay, or the stopping potential or rest potential or open circuit voltage for this cell, okay. And then if we further increase it, then the reverse reaction will happen, right? You know that. And this reaction will happen in the other direction also, meaning this addition of these two, okay, is perfectly reversible. Now I'm going to give you an example, okay, which is not reversible. So this example, okay, is an example of a reversible chemical reaction or electrochemical reaction, whatever. Okay. Now you know what is the meaning of reversibility. Okay. Chemical reversibility. Let me give you another example. Another cell, let's say this one. G H plus sulfur and okay. So what we have actually zinc metal, okay, on one side. I have platinum on the other side, and basically I have acid, okay, H2SO2. Okay, clear? Aqueous solution of H2SO2. So that will also constitute a cell, because actually zinc and platinum will have very different electromotive force, or basically different potential. Okay. So if you connect it, you will get electricity, and if you reverse it, you will see what is happening. Okay. If you just connect it, if you just short these two electrodes, okay, the reaction that will happen is that zinc has what is the electromotive force of zinc? Minus 0.77, right? 0.76, okay, with a minus sign, right? So basically, as you can see, for this thing, this is the left electrode. Okay, see, that's how I have written it. For the earlier one, actually, this was 0 and that was positive. Okay, now this is negative, that will be 0 basically. Okay, so what I'll have is zinc, of course, you know that I'll have zinc 2 plus, right? And then the hydrogen reaction already you know that I'll have 2H plus 2 electron. Okay, so this will happen. Now this is happening at zinc electrode, and this is happening at platinum electrode, right? In the forward direction. Now the forward in the sense that I'm not actually applying any voltage. Okay, this is the spontaneous direction. Now the question is, if I now keep on applying, okay, voltage in the reverse direction, at some point this will stop, okay, and then something else will happen. Then what you will see that, think about it, I have actually zinc, okay, 0.77, okay, minus 0.77. But then if I want to reverse the reaction, there is also water present here, okay, and then water also can oxidize, okay. So then what will happen, a very interesting thing will happen, for the zinc, now you will see this reaction, okay, will happen at the zinc electrode, okay, and for platinum we have yeah, and this will happen at the platinum electrode. Now see, these things, okay, are not opposite to each other. Okay, so the entire thing has totally reversed. Okay, so which means this is not an example of a chemical reversible reaction. Now, if it is chemically not reversible, okay, it is of course not thermodynamically reversible. Cannot be, right? But if it is chemically reversible, it may or may not be thermodynamically reversible, because suppose if the electron transfer is extremely fast in one direction, okay, and the reverse actually is not very easily attainable, okay, which means actually each step I am not actually maintaining the equilibrium, so it may not be thermodynamically reversible. In fact, actually most of the chemically reversible cells are not actually in true sense thermodynamically reversible, because thermodynamic reversible means it's a little bit change is happening, okay. But for practical purposes, we will just take this kind of examples, okay, where actually I have the reversibility, okay, and then we will not consider these reactions. There is another way of thinking of it. We'll just see in a while that we'll use the Nernst equation, right? And the Nernst equation actually comes from chemical equilibrium. So we have a reductant and oxidant, right? So that is in equilibrium, which means actually there is an inherent concept of reversibility. Okay, at least chemical reversibility. Okay, and we are assuming that if the system is chemically reversible, okay, it will also be thermodynamically reversible. But thermodynamic reversible, actually the conditions are much more strict. You know that, because reversibility is basically an idealized situation, right? In reality, you never see reversibility. But we are also assuming that if it is chemically reversible, it will be thermodynamically reversible. So sometimes these kind of systems, we call it as a practically reversible systems. Okay. Now, whatever it is, okay. Now let us consider another interesting thing. Okay. Now think about it, this thing which I am writing on the board, like H plus, okay, going to H2. Now this we could actually construct even from thermodynamic data, right? Like our Hess's law and all these things, right? I could actually combine many different reactions, and then if the net stoichiometry matches with one of them, okay, just from the energetics I can actually calculate the delta H, right? So I can actually get a thermodynamic data, okay. Now let us consider a very interesting situation, okay. So let's say this thing, okay, this is an overall reaction. We already gave you this example, okay. So I have zinc and basically silver chloride electrode, okay. And then suppose this is the spontaneous reaction, okay. And I am telling you that basically if I do it from thermodynamics, okay, I will get something like say minus 233 kJ. This is the thermodynamic. Now how do you measure the 233? Like you can actually think of an experiment something like I have the entire cell, okay. Entire cell means I have two electrodes, okay. One is zinc, one is basically silver, and this is the net reaction, what is happening, okay. And this thing I can actually dip in a calorimeter, okay. Now if I dip it in a calorimeter, I will see a temperature rise, and if I know the material of the calorimeter, I can always know the specific heat. From that I can calculate what is the heat of the reaction, okay, which also matches with the thermodynamic data, okay. We are doing, and we are basically trying to make everything conceptually very correct, okay. Now, so what I just said is that I have a cell, right, and then basically electron is flowing in some directions, okay, and I'm just asking what is the basically this is molar, okay, pollution per mole. It's a molar heat LC, okay. Under standard condition in the sense all the species have unit activity, okay, like zinc 2 plus and all the chloride ions, they're all in unit activity. That's why I'm just writing delta H, okay. Also the temperature and the pressure are basically standard condition, okay, clear? Now suppose I want to make, okay, just for the sake of the argument, I have to make it reversible. Now think about it, if I just short these two electrodes as I said, okay, with an external circuit, so electron will flow and there will be a gradient of electron flow, right? There will be a potential gradient. Now that is not very much reversible because if the gradient is very steep, okay, ideally then actually to make it reversible it's very difficult, okay. So what I have to do is that I have to make somehow this potential gradient not so steep. In the sense like electron flow, I have to make it slower. Okay. What I can do very quickly is that I can actually put a resistance. Okay. And then suppose I am repeating this experiment. So basically I have a resistance. Now when I have a resistance, okay, there will be another thing also. I'll basically have this excess energy lost as heat. I could have actually attached a bulb, then it will be lost as light energy, whatever. Okay, clear? I'm also taking the energy out of the system. Okay. Now you may ask what happened to the actual energy. Actual energy will also be dissipated as heat. Of course, because this is ultimately is a thermal energy. Okay, basically electrical energy being converted, okay, into chemical energy, but that energy conservation tells me that there is a thermal energy, there is electron flow. Okay. But I can actually have another source of dissipation. Okay. Now suppose if I repeat this experiment in a calorimeter, okay, I'll see actually same values because actually conservation of energy tells me that I should not have anything. Okay. But let us now try to think that conceptually, suppose I am doing an experiment where I measure this thing inside one calorimeter, okay, and I measure this thing in another calorimeter. Meaning, what I am doing is that I am just measuring how much heat is dissipated across this resistance, okay. Plus I am measuring how much was basically the total, what was basically the total heat change, okay. Now together, we'll see what is happening, okay. Now, the thing is that suppose there will be some heat change, right? So suppose I call it as a QC, C for it is cell, okay. And this is basically, let's call it as a QR, okay. This is a resistance, okay. And this is the cell, okay. This has of course two electrodes. Now the way I have written it, it is delta H is negative in the sense that it is exothermic, it is producing heat, right? So what I'm trying to say is that depending on the R, okay, the amount of the resistance I have put, okay, so these two things will change, the heat partitioning will change, okay. For example, if I have R equal to 0, something like a very initial thing, okay, so I will not have any heat, almost 0, okay. But if I actually keep on adding resistance, okay, I will see actually I can reach a limit, okay, where basically the resistance is almost infinite, meaning you are putting a lot of resistance, something like that, okay. And then the electron flow will be slower, but this slowness also has a limit. It cannot be infinitely slow, okay. Which means that I have reached somehow like the reversible limit, okay, for practical purposes. So if I have reached the reversible limit, okay, so this heat change now, okay, should be reversible heat change, right? So let me just write it down, okay. So all these heat changes are actually will have then the reversible heat change. Why? Again, basically I'm trying to actually impose the reversibility, okay. Now think about it, for the cell, right? So let me just write down the value, okay. So in the limit of R tends to infinity, these are all these are all experimental data, okay. So if I have a very high resistivity, QC reaches a value something like minus 43 kilojoule per mole, and QR reaches something like minus minus 1. Okay. Yes, sir. Yeah. Now think about it. Like what I did is that I just divided the heat, okay, into two parts, and one is across the resistance, and one is basically within the cell. Okay, both are in. Again, you could have done another experiment, or actually you could use a electrical work, like a light bulb or whatever. Okay, this is just an example. Okay, how much is this going? When I have reached basically an infinite resistance kind of limit. Okay, so the cell is now acting reversibly, and I can actually use thermodynamic principles. Okay. Now the question is, fine. Earlier, the way I was measuring it, it was something like an isolated system. The system immersed in a calorimeter, the entire thing. Okay. Now this is basically kind of two systems. Okay. Now think about it. What is delta G? Right, Gibbs free energy change. Which we told that Gibbs free energy change is basically the non-PV work. Okay. Now what is the non-PV work? This is the non-PV work. Here actually we are just heating it up. Okay, I could have actually used a bulb. Okay, and I could have actually drawn some light energy. Okay. So this actually amounts to my delta G. Okay. So this is equivalent to basically my delta G. Okay. And this, of course, this is under standard condition, so I should write it as a delta G0. Okay. And this thing, okay, the reversible heat change inside the circuit, okay. I know that if the temperature is fixed, that is nothing but temperature times delta S. Okay. So this is nothing but T delta S0 kind of thing. So if I now add actually, okay, like that is delta G0 and delta H0. Delta H0 will be delta G0 plus T delta S0. Okay, I get the same value basically, 233. Okay. Now this is the way you have to think about the problem. Like I have a electrical circuitry. Okay. And then what I'm doing actually, I'm doing some work. Okay. Now once you want to do an usable work, okay, you have to basically extract that. Okay, either you put a bulb or you do something. You could have actually charged a capacitor, or you could have done something else. Okay, run a motor. Here actually we have produced heat across the resistance. Okay, that's basically the usable energy I'm getting. Okay, which is a non-PV energy. So by definition, that is my delta G0. Okay, which is getting out from the system. Clear? But I have to do this work. Okay, some entropy change associated with the system. okay, which is happening in the cell. This will happen only in the reversible limit strictly. Okay. So then actually I can understand basically what is the meaning of this partitioning. Okay. And what is the meaning of this reversible condition. In this case the reversibility means actually the resistance going to infinity because the electron flow is very, very slow. Okay. But again, we usually do not use this condition because these are not very practical conditions. In practical conditions, we will assume that if the reaction is reversible, okay, the thermodynamic reversibility is also holding. Okay, clear? All right. Now again, we can use the same reaction. Alright, so this was basically the spontaneous direction, right? Now how do we calculate basically the free energy change or the magnitude of the free energy change? Okay, so energy, think about it. Energy is nothing but, this is a non-PV energy, as I said, right? Here it is a electrical energy. Electrical energy means basically if you have a potential difference of delta phi, okay, it will be just a potential difference and multiplied by the amount of charge carried, right? So I can actually write it basically the charge, okay, carried or charge basically passed, okay, times, I'll just write the potential difference, but this potential difference has to be the reversible potential difference. Okay, because actually you are talking about a thermodynamic quantity, which is delta G. Okay. Ideally, it should be the reversible potential difference. In the sense that if I just quickly, okay, change the direction by applying a voltage, at every step, I can actually maintain the reversibility. Or the system is basically maintaining equilibrium as it is passing, which is not, again, true in the practical sense, but we are thinking it to be like that. Okay. Otherwise, we cannot actually connect this thing to thermodynamic parameters. Okay. So of course, you know what I'm going to write. Okay. So basically, the suppose that with the potential difference, I write it as E. Okay. Or I'm just writing something like that. Okay. And suppose the charge passed, if I just call that n moles of electron has passed, each mole I know that the amount of charge will be basically 96,000, how much? 584, right? 584.56, something like coulomb. Okay. And then basically this will be the equation. Okay. Now the thing is, usually like this part, okay, think about it. This is a constant. N is constant, F is constant. Okay. So this is just the amount of charge. But now E, okay, E is basically potential difference. Okay. Now think about it. Difference is like just quantity which we like cannot use usually in a sense. Like it is not a positive or negative quantity. It is just a difference. Meaning if I just call it as a platinum electrode is somewhere here and another electrode is somewhere here, right? You do not talk about what is the direction of it. Okay. But whether this difference is positive or negative, that will dictate whether the process is spontaneous or not. Because thermodynamic processes has a sign convention. Okay. But usually electromotive, like whenever I am talking about electrical work done, okay. So then the potential difference is just, like if you read any physics textbook, right? We just write it as a delta phi notation which does not have any, sign convention. Okay. But just to make the thermodynamic thing and this thing correct, taking the example of this reaction, okay, we'll follow something like, look at what is the spontaneous direction. Okay. Now in the spontaneous direction, I know by my convention delta T should be negative. Okay. Like this thing should be negative overall if it is spontaneous. Okay. So by that choice, now the question is, now what I'll choose for the sign of this. Okay. So the convention we use is that, okay, fine, this electromotive force is positive if I just connect it and if I see an electrical energy flow. So if this is positive and this thing is negative, basically I can modify this equation as we always know already. Okay, we always write it like this. Okay, but in an older convention it was basically plus NFE. Okay, why plus NFE? Because that E was basically the other way around. Okay, delta G in thermodynamic convention is always negative. Okay, whichever convention you use. Like work done by the system is positive, work done by the system is negative. Okay, delta G is always negative. Okay, for a spontaneous process. Now, the second convention is that how you should choose the E. Okay, and this has a direct connection with our choice that why we choose always the standard reduction potential. We always write right minus left, the electromotive force. Okay, and that we take to be positive. So you always write basically the word it's basically right electrode minus left electrode that way. Okay, so that is basically a unique convention. Okay, sorry, that is not a unique convention. There were other conventions, but this is a convention everybody uses. Okay, now again the thing is that it has to be reversible because otherwise this convention also doesn't have any meaning. Why? Because as I just said, that the potential difference, okay, I can create a potential difference in the positive sense or in the negative sense. Meaning I can make this process as a going in a spontaneous direction or in the other direction. Like all these discussions are possible if the process is reversible. Okay, which means the reaction also has to be reversible. Okay, for the irreversible reaction, the example I gave you, I cannot actually write all these things. Delta G is equal to minus NF, right? All right, so the moment we have it, then actually we can have delta G is minus NFE, or like if everything is done in a standard condition, I can actually use a similar notation. Okay, it is something like minus